Hello everyone, I'm Hari. I'm here to present our work on logical characterization of coherent uninterpreted programs or CUPS. This is joint work with my supervisor, Professor Harry Gurfingal at the University of Waterloo and Professor Sharon Schramm at Tel Aviv University. So let's get started. We are mainly interested in uninterpreted programs. These are programs where you abstract function definitions. The only thing that you know about functions is that they follow the coherence axioms. We forget what the functions actually mean. We just abstract them by saying that the only thing we know about them is the coherence axioms. It's the congruence axioms, sorry. Now, uninterpreted programs are a natural abstraction layer for software. It has many applications, including in equivalence checking and global value numbering. While these abstractions might seem very simple, it is theoretically very interesting because the reachability problem for uninterpreted programs is undecidable. Now, a couple of years ago, in Popel 2019, a subset of uninterpreted programs called Coherent Uninterpreted programs was introduced, and it was shown that the reachability problem for CUPS is decidable. In fact, the paper also presented several extensions, and several follow-up works contributed a lot more to coherent uninterpreted programs. For example, they defined what are k-coherent programs. They showed that checking whether a general uninterpreted program is coherent is decidable, and so on. So when we were reading this work, we were very curious as to how inductive invariants of CUPS look like. That brings us to this paper. In this paper, we logically characterize the inductive invariance for coherent uninterpreted programs. What this means is that this is an alternative proof of decidability of reachability for CUPS. And furthermore, because of this logical characterization, we can now design algorithms that are both sound and complete for CUPS while still being sound for general uninterpreted programs. Now, such algorithms don't have to differentiate between CUPS and general uninterpreted programs, so you can save some time. You can save the time spent to check whether a given program is coherent or not. Now, as we wanted to prove logical characterization, we ended up proving that CUP programs are bisimilar to finite state transition systems. This implies that not just reachability, but all temporal model checking properties are decidable for CUPS. Okay, before we get into detail about our contributions, we have to make sure that we are all on the same page. So we first present the syntax of the programs that we are talking about. The syntax is very straightforward. We allow all keywords like while, assume, if then else, and so on. To keep things simple, we say that whenever you have a conditional, it can only have it cannot be a combination of conditionals. It has to be either equality or disequality. This is not a restriction because you can achieve combination of conditionals using if then else statements. Similarly, we only allow functions applied to variables. Again, this is not a restriction because you can add more ghost variables to add more variables to represent deep function applications. Here is a formal semantics if you want to look at it. Here is a formal syntax of CUPS if you want to look at it later. Okay, so what are the semantics of uninterpreted programs? We use standard small step semantics. This is very common in, for example, symbolic execution. I'm just going to explain the assume statement and the assignment statement. I emphasize that everything is pretty standard. So let's take the assume statement for example. So let's say your program reached a configuration. Assume C, Q, PC. So Q is a state, a mapping from program variables to constants in logic, and PC is a path condition. So this program when you reach this program configuration, you first evaluate the conditional C on the state Q. This will give you an expression in logic P. you check whether V is consistent with the current path condition, and if so, you conjoin the expression with the path condition. Okay. And for the assignment statement, you do almost the same thing. You take the right hand side, you evaluate it in the current state, you get an expression, then you first update the state by remapping the program variable to a fresh constant, and then you update the path condition to reflect this. Again, this is pretty standard symbolic execution semantics, but just to make it extra clear, I'm going to go through an example quickly. When you start, we have a special initial state which maps all program variables to special constants annotated with 0, and the path condition is true. Once you start executing, you update the state. Now x is mapped to x1 and the path condition is updated to x1 equal to t0. You keep executing. If you take a while loop, then you assume that the condition for the while loop is true. So in this case, you assign that c0 is not equal to d0. You keep executing. As you keep executing, you keep updating the state and you keep adding more things to the path condition. Now, the path condition kind of stores the history of your execution. So if you just look at the path condition, you know how many times the while loop was executed, for example. Here you can see that the while loop was executed m-1 times, and in the mth iteration you assume that cm is equal to d0 and you exit the while loop. Notice that even though the path condition only contains one level deep terms, it implies a more complex relationship between the constants. For example, this PC implies that xn is n of n of n of n of x0, even though we only see one level deep function applications. Okay, now once you have the path condition, the question is, or once you have the semantics, the question is, how do you summarize all program behaviors? To do this, we use the standard inductive assertion maps. So inductive assertion maps are basically inductive invariants, except you have locations as well. So inductive assertion map is a mapping from program locations to formulas in a UF. It has to satisfy the initial condition, which is that at the initial location, the inductive assertion map is true, and it has to satisfy the inductive condition. So if you reach a program configuration at a location P at a state Q and the path condition at of P, and then you take one step to a new configuration P prime, Q prime, PC prime, then it has to be the case that PC prime models the PC prime satisfies the inductive assertion map at the new program location. Of course, if you want to prove that some program location is unreachable, all you have to do is come up with an inductive assertion map that assigns that location to false. In our example from earlier, this is what an inductive assertion map will look like. If you look at line 1, after executing line 1, the only thing that we know is that x is equal to t. Maybe something that is more interesting is lines 4 and 5. So let's say that after executing line 4, the inductive assertion map says that x is equal to n of y and c is not equal to d. Then if you execute line 5 and that is update y to n of y, then you know that x is equal to y. So this is an example of an inductive assertion map for our example program. Maybe what is more interesting is line 10, where you assume that a equal to b. The inductive assertion map says that variable a equal to b and x equal to y and c is equal to d. Therefore, you cannot execute line 11 because you are going to assume that x is not equal to y, and hence the inductive assertion map for line 11 would be false. Okay, so now we are at a point where we can understand what logical characterization means. Precisely what we mean is that we can capture the set of all reachable states of coherent uninterpreted programs using an inductive assertion map of depth less than or equal to 1. Now, this result is non-trivial because the path condition, as we saw earlier, can imply very deep relationship between constants. Okay, but to understand the results better, we need to understand what cups are. I have not defined it yet, so I'm going to define it now. As I mentioned earlier, cups are uninterpreted programs restricted in two ways. The first way is memoization. There is a complicated definition here. I'm not going to go over it word by word. Instead, I'm just going to give an intuition. Memoization basically means that you cannot recompute terms that you have already forgotten. Okay? Let's just look at this example to understand memoization better. So in the example on the left, you have you first assume that x is equal to w, then you compute a term n of x and then store it in y, and then you forget n of x by reassigning a y to a new variable a, and then you try to recompute n of x by computing n of w, because of the assume n of w is equal to n of x. So at line 4 you're essentially recomputing something that you have already forgotten. Memoization just says that you can't do this. Okay, so if you want to reassign something, you have to store it in a variable. So in order to make this program memoized, all you have to do is right before you reassign y to a, just store whatever you have in y to a temporary variable t, and now when you execute z is equal to n of w, you already have n of w stored in variable t. Okay, so there is no recomputation of things that you have forgotten. Okay, so that's one of the restrictions for cups. The other restriction is early assumes. Again, I'm not going to go into this definition word by word. Instead, I'm just going to give an intuition. So on the program on the left, I'm claiming that the assumes are not early. What does it mean that assumes are early? It means that whenever you assume that two variables are equal, all the super terms of these two variables are already stored in program variables. That's what it means for assumes to be early. So if you look at the example on the left, you have variables a and b, and you have a while loop. So a and b are assigned to x and y, and you compute n of x and n of y and super terms of x and y in the while loop, and then at line 7 you assume that a is equal to b. And here we say that this assume is not early, because a and b contains the first values of x and y, and then many super terms of x and y are computed in the while loop, and after all the super terms are computed and forgotten, you assume that a equal to b. So to make this assume early, you just have to push it before the loop. So at line 3, before you computed any super term of a and b, you have to assume that a is equal to b, and then you're free to compute and forget all the super terms of a and b that you wish. Okay. Now, our running example from before is indeed a coherent uninterpreted program, because it satisfies both memoization and early assumes. Now you can see that there is no term recomputation here, because you are computing bigger and bigger terms inside the while loop. So we satisfy the memoization property trivially. To see that we satisfy early assumes, we have to look at the assume statement at line 10. It assumes that variable a is equal to variable b. Now there are two super terms. There is a super term for a, which is f of ax, and super term for b, which is f of by, and we can see that both of them are stored in variables when you assume things. So we satisfy early assumes in this case. Now there is also an implicit assume statement for the while loop. That is, as you exit the while loop, you have to assume that c is equal to d. That also satisfies early assumes, because there is no super term of c when you exit the while loop. Okay. Now, why is reachability of cups decidable? In this slides, I'm trying to convey the intuition for why we have the logical characterization that we have. So in some ways, this is the most interesting part of the talk. Okay. So reachability of cups is decidable because of both early assumes and memoization. Let's take an example to see why this is the case. So let's imagine that there is some code snippet, and somehow in the first few lines you assign c to f of x and d to f of y. That is what you have in the congruence graph on the right hand side. You have you have constants x and y, and you have c equal to f of x and d is equal to f of y. And at some point you assume that x is equal to y. Now what early assumes guarantees is that you will definitely have two program variables, a and b. They need not be different variables, they can be the same variable, but both of them would be equal to f of x and f of y respectively. Okay. Now what does this give us? Since we are sure that there is a and b, we can be sure that we need only remember that c is equal to f of a and a equal to f of x. We don't have to remember that c is equal to f of x. Okay, so we don't have to remember this deep relationship. We can just remember this one level function application. Now, so I'm saying that we can safely forget that c is equal to f of x. But then you would think that, oh, what happens if I reassign a and b? This is allowed by both memoization and early assume. You can reassign a to some other variable t and b to some other variable u. Now, even though c is equal to f of x, you have forgotten this fact because you only kept track of the relationship between c and a, and since a has been reassigned, you have completely forgotten the relationship between c and x. Now you would think that you can assign a new variable e to f of x, and then aren't we missing the fact that c is equal to f of e, right? Because c was f of x and e is f of x. This is where memoization comes in, and it says that you cannot recompute things that you have already forgotten. So once you have forgotten that a is equal to f of x, you cannot say that e is equal to f of x again. Okay, thus from early assumes and memoization, we gather that we only have to keep track of variables and one level function applications. So even though your path condition can have a lot of terms, we are only concerned with what are the constants that are currently stored in program variables and what is the relationship between program variables and functions applied to program variables. We're not interested in functions applied to program variables or any other deeper terms. Okay, we capture this fact using an abstraction called V-based abstraction. Once again, what we want to capture is all equalities between program variables, all disequalities between program variables, and equalities and disequalities involving functions applied to variables. Now, how do we capture this? We capture this using a congruence closure graph. We draw the congruence closure graph. We represent as many equivalence classes as possible using program variables, and we just forget all the other equivalence classes that are not represented using program variables. Okay. Once again, I'm not going to exactly define this V-based abstraction. Instead, I'm going to run you through a couple of examples to get an idea of the intuition. So let's assume that you are executing a program and you reach a state where PC is x1 is equal to f of x0 and y1 is equal to f of y0 and x0 is equal to y0. And your current state maps x to x1 and program variable y to constant y1. So our abstraction would first draw the congruence graph, compute the closure, and just forget all the equivalence classes that are not represented by current program variables. Okay, so our abstraction in this case is going to be x1 is equal to y1. In particular, we forget that x1 is some nested application of f to some other constant. We completely ignore that fact, and that is our abstraction. Now, you might think that this is very easy, but there are some trivialities here. In particular, when it comes to non-unary functions, things get a little bit complicated. So let's take another path condition. So here you have x1 is f is a binary function applied to a0 and x0, and y1 is f applied to b0 and y0, and x0 is equal to y0. And we have to forget x0 and y0. Okay. So one way to do it would be to this congruence closure graph does not imply any relationship between x1, y1 or a0, b0, right? So if you compute the congruence closure graph, there is no other lines to draw, and if you just forget everything that is not related, so if you forget x0 is equal to y0, then there is no relationship between x1 and y1. So this is what you would get. So an abstraction that just forgets this x0 is equal to y0 would just give you true. But in fact, it actually misses something. So let's say we have x0 is equal to y0. Let's say we have a0 is equal to b0 as well, which means that if a0 is equal to b0, then x1 is going to be equal to y1. So there is something there. So there is a relationship between x1 and y1, namely that if a0 is equal to b0, then x1 is equal to y1. So our abstraction should not forget this, because once you exit this PC, the next statement could be assume a0 is equal to b0. Right? So we can't forget this fact. So we capture this by using fresh constants to represent equivalence classes that we are going to forget. In this case, the equivalence class that we are going to forget is x0 is equal to y0, and we use a fresh constant w to represent this equivalence class. And now our abstraction would be x1 is equal to f applied to a0w, and y1 would be equal to f applied to b0w. In this case, if you assume a0 is equal to b0, then we get that alpha q of pc implies alpha q of pc, and a0 equal to b0 implies x1 is equal to y1. So, and this fresh constants is a non-trivial result of our abstraction. Okay, so I hope you have gotten an idea about our abstraction. Now, the main theorem that we state in our paper is that for a coherent program, the abstraction that we just defined induces an actual bisimulation relation. And we further prove that this base abstraction is finite. That is, you don't have to introduce infinitely many w constants when you do the abstraction. Okay, so let's just pictorially look at what our theorem looks like. So on the right you have this program, and on the left you have the translation system introduced by this program. Now the translation system has infinitely many states. In particular, you can execute the loop 0 times, 1 times, 2 times, or any number of times. And even depending on the number of times you execute the loop, you can reach program location 8 in infinitely many configurations. If you abstract each of these states, you will get a finite bisimilar translation system. It will have just these many states, and it looks much more compact than the infinite state system. Okay, how do we make use of this bisimulation relation? We say that we can logically characterize cubs by just looking at the finite translation system. So you can generate an inductive assertion map for cubs by just looking at this finite translation system. Now this is very straightforward. You just look at all the states of the system. Since this is a finite bisimilar system, you can just look at all these finitely many states and just write down the formulas corresponding to it. Except you have got these w constants that have been introduced by the base abstraction. Okay. And in the paper, we prove that we can get rid of these w constants using cover or uniform interpolance. And we prove that removing them will not increase the depth of the formulas. Okay. So this is how you would write down the logical characterization. You will look at the bisimilar system, and you look at the location, and you take the formula here and put it in the inductive assertion map for the coherent program. Okay. Now, what is interesting is line 9, where the bisimilar system has these fresh constants w, and when you eliminate them using cover, you get a formula with implication like so: a equal to b implies x equal to y, and this does not increase the depth of the formula. I just want to point out that there are many more details in the paper. In particular, there are formal definitions and proofs, and more details about the base abstraction. We prove that base abstraction is finite. In fact, it's not straightforward to see that base abstraction is even computable. This computability depends on naming W's carefully. I encourage you to read the paper to find out how to name W's in the right way. We also prove that eliminating W's does not increase the depth of formulas. Okay. Finally, an interesting comparison is how do we compare to the previous proof, paper presented at Popel 19. The previous work used automata construction, whereas we use a logical characterization using a bisimilar transition system. We believe that our proof is simpler. In fact, as we were looking deeper into this work, we found out that there are two issues with automata construction in their paper. We contacted the authors and they confirmed that the issues we found were indeed real issues with the proof in the paper. And one thing that we present that is not presented in the previous work is that we prove that cups are bisimilar to finite state systems. Okay, to conclude, cups are an interesting subset of uninterpreted programs whose reachability is decidable. We give a logical characterization for cups, and we prove that cups are bisimilar to finite state systems. Thank you.